nanohub.org.
Online simulation and more for nanotechnology.
So this morning what I'd like to do is to try to pull together everything that we talked about yesterday and pull it into a model that includes both ballistic transport and scattering, and then in the next lecture take a look at what the future might hold for nanotransistors. So I'll call this a scattering model. And just to remind you, we're using this Landauer approach. This is our starting point. We have this simple description of current flow that involves some fundamental constants, 2q over h. It involves this quantity called transmission that we've got some feeling as to what it is now, just a number between 0 and 1. It involves a number of channels at a particular energy, so this depends on what the band structure of the material is, or if it's a molecule, we can compute the number of channels there. And it depends on the Fermi levels of the two contacts. So there's always an assumption that we have these special type of contacts called Landauer contacts that are maintained in thermodynamic equilibrium, that have well-defined Fermi levels and inject electrons into the device. And we have an expression that works under any bias, and we have a simplification that works under low bias. And we went through an application of that expression to the MOSFET, and we arrived at these results. So we had an expression for the linear region current. Current is proportional to voltage. We had an expression for the on current, and we have actually a full range expression. We can go from low VDS to high VDS. But that's ballistic, and we saw that for most transistors, especially silicon transistors, scattering is important. So we talked about scattering, and the basic idea is, in the end, all we want is this number T, this transmission. So all of the microscopic scattering physics ends up being expressed in terms of the probability that an electron ejected from the source will come out at the drain. That's a number T between 0 and 1. And we saw that there's this very simple expression. If I have a region that doesn't have a high electric field, and if I have a constant mean free path in that region, lambda naught, then the transmission is just mean free path over mean free path plus length. And this actually, in practice, we've looked at it in a lot of different cases where we compare it with a lot of much more sophisticated calculations. It seems to work better than it should, but it's a pretty good description of scattering. Okay, so we might think that it's easy. All we do is we take those ballistic results, we multiply by T, and we're done. And there's a little more to it than that. So we'll talk about that a little bit. Now, it turns out in the linear regime, that's all there is to it. So in the linear regime, we just take the ballistic current and we say not all of that current that was injected at the source comes out the drain. We just multiply it by T, and there we have it. So that part is pretty easy. We know what T is, so we can compute the current. If we know the mobility of the semiconductor, we saw that the mobility is related to the mean free path. So from the known mobility, we extract the mean free path. From the mean free path in the channel length, we compute T. We plug it into the equation we had for the ballistic MOSFET, and we've got an expression. Okay, so let's just take a look. It might be curious. What is T for a modern MOSFET? So we can do some back-of-the-envelope calculations, right? I've learned. Back of the envelope is not a phrase that people know anymore. Do you know what back of the envelope is? People used to do a calculation. They would find a piece of paper, or it was an old envelope, and turn it over and do a quick calculation. Just quick. All right, so we have, let's say that the mobility in a modern MOSFET is about 200. Right? That's close for a current day MOSFET, in the range of 200 to 300. We had this expression that relates the mobility to the mean free path. That expression is actually only valid in Fermi-Dirac statistics, Maxwell-Boltzmann statistics. But we could correct it with a couple of Fermi-Dirac integrals if we wanted to do a little bit better. But if you just use that, take the measured mobility, equate it to the formula in the second line, and deduce what the mean free path is, it's about 9 nanometers, 10 nanometers or so. Okay, right? You know, say the latest MOSFETs have about 22 nanometer channel lengths. So the channel length is about 2 mean free paths long. That's in this gray area. It's not long enough to be diffusive, where you really feel comfortable in using a mobility. It's not short enough to be ballistic. You know, that's where we are today. So about 30% of the electrons that come in from the source go out the drain. You know, modern nanoscale MOSFET under low drain bias. Okay, now let's look at high drain bias, because here the story gets a little more interesting. You might think that, okay, all we have to do is multiply by T again. Okay, but that doesn't work. So let's see why here it doesn't work. So here's the situation we have. When we have a ballistic device, we inject some flux of electrons from the source. I'll call that I+. They come in and they flow out the drain. The charge at the top of the barrier consists of electrons with only positive velocities under on-current conditions. Because all of the electrons come in from the source with positive velocities, they fill up the positive plus K states. So we only have that half of that Maxwell-Boltzmann distribution. What comes out is just T times what got injected in. All right, no problem with that. Okay, but there's also some backscattering, and that turns out to be important to think about that. So the fraction that doesn't come out is 1 minus T. You can think of that as reflected by scattering. It turns around and goes back to the source. So it means that the total charge at the top of the barrier now has two parts. It has a part due to electrons with positive velocities that came from the source. It has a part due to electrons with negative velocities that came from the source, were backscattered and turned around. So we've got both plus and negative velocities. What that means in practice, oh, we're finally getting some rain. What that means in practice is that in order to get the charge that we need, which MOS electrostatics says is always Cox Vg minus Vt, that's never going to change. But now we can inject less positive flux because we're going to get some negative flux too. And we'll add the two together. Okay, so we won't be injecting the same flux that we did in the ballistic case. So let's see how that works. In the ballistic case, we injected some positive flux. I'll call that I plus ballistic. And current is just charge times velocity. So if I divide that injected current by width times thermal velocity, that's the charge at the top of the barrier. Under ballistic conditions, it only positive velocity electrons. Okay. Okay, now when I have scattering, okay, what I have to do is I have a positive flux and I have a negative flux. And both of them contribute charge, so I've got to add the two together. I'm going to make an assumption here. It's not completely obvious. The positive flux comes in at the thermal velocity, right, out of the source. When it backscatters, you know, what's its velocity? I'm going to assume it's about the same, right? And detailed simulations show it's close. So I'm assuming that the backscattered flux is traveling at the same velocity. So if I want the total charge, I just divide the positive flux and the negative flux. I add the both together. I'm not subtracting them. The net current, I would subtract them. But I'm adding the two because they both give me carriers. And that's my total carrier. Now, MOS electrostatics is going to demand that those two Q's be the same, whether I'm ballistic or whether I'm diffusive, right? It doesn't care what's going on. The Poisson equation just wants the charge to balance. Okay, so I can equate the first two equations, and I can solve for I plus in the presence of scattering, and I can relate it to I plus in the ballistic case, and we find out, let's say T is 1/2, then downstairs I've got 1.5. So I'll have less positive flux injected when there's scattering, because I'll have both halves of the distribution. So that's my positive flux that gets injected when I have scattering. What comes out is just transmission times positive flux. So I have to multiply that by T, and I find my on current is not T times the ballistic on current. It's T over 2 minus T times the ballistic on current. Okay, so all of that comes in from MOS electrostatics. You probably, if you were familiar with Landauer and you were comfortable with all of this stuff, this is probably the thing you would have missed because you wouldn't have had MOS electrostatics in it. Again, it's an example of how important electrostatics is in this device. Okay, so we have an expression. Now we just take our ballistic current expression and we multiply by transmission over 2 minus transmission. Okay. All right. And now we have both range. We could actually do a full range too. We could do a calculation that would go to the right limits in both categories, and that the expression is here, but it's not quite that easy. And the reason it's not quite that easy is, as we'll see in a minute, T is actually changing as a function of drain bias. So one of the pieces of unfinished business here is how you calculate that entire curve. Right? How you get a model for that. It's a little bit difficult to do. Okay, but we have it, and we know how to put scattering in. It's a little more involved than just multiplying by transmission, but it's not too involved. So now we have a scattering model. Okay, so let's go back and look at one of these comparisons. This was this extremely thin SOI MOSFET that we were looking at, 40 nanometer channel length. The red lines are a ballistic simulation. The dots are the measured results. And we showed before that when you subtract out the series resistance and things and look at that a little bit more carefully, the linear current was about 20% of the ballistic current, and the on current was about 60% of the ballistic current. And then the question is, what is the transmission for these devices? Okay. So we have the linear regime, and we have an expression for the linear current, and we have the on current, and we have an expression for the on current. So what that expression tells us is that the ratio of the actual current in the linear regime to the ballistic current in the linear regime is just a transmission. So if we can estimate the ballistic current, measure the linear current, divide the two, we've got the transmission. Okay. And that ratio, so that transmission was 0.2. Now, under the on current conditions, the ratio of the measured on current to the computed ballistic on current is not T, it's T over 2 minus T. And now, I've separated that these T's aren't necessarily the same under low bias and high bias. So we want to talk about that. In fact, if you just calculate these, you find T linear is 0.2. So in this particular device, about 20%. Remember, my back of the envelope calculation said in a 20 nanometer device, about 30% of them transmit across under low bias. This device is 40 nanometers long. About 20% of them are transmitting across. Right? So it roughly makes sense. And this is the thing that's really interesting and a little surprising about this device. Under high bias, when the carriers are more energetic, the transmission is higher. You'd think there'd be more scattering and the transmission would be lower. It's just the opposite of what you expect. Okay. All right. So, how do we understand that? So here's the situation. When we have low drain bias, this is the situation. That dotted line is my energy band diagram. Under low bias, there's just a small difference between the conduction band and the source and the drain. Electrons are injected. We have our expression. They're injected into a region that has no electric field. We have an expression for the transmission. All right. Everything works fine. If we took the measured mobility and we estimate the transmission from the measured mobility, it's about what we get when we look at the ratio of the ballistic and measured on currents. Now, if you look at under high bias, okay, now the question, it's much more complicated. If you want to do this problem properly, we really need one of these Monte Carlo simulations like the results I showed you from IBM. And this is a very complicated problem to treat transport here. This non-local transport, velocity overshoot, all of these things going on. The electrons get a lot of kinetic energy when they get over that barrier and head to the drain. They scatter a lot. Their mean free path is really small. You know, when I take the mobility, I'm talking about electrons that have an average energy of 3/2, or have an average energy of kT in 2 dimensions. You know, that's really small, 0.026 eV. If I apply a volt to the drain, the electrons have about an electron volt of kinetic energy when they get to the drain. They have a lot of energy. They scatter a lot. Their mean free path is really short. And it's varying spatially from the source to the drain. So if the mean free path is really short, you would expect that the transmission would be really low. But the transmission is even higher. Okay, all right. But the reason that that occurs is that when we talked about scattering, we talked about how high field regions are good collectors. If an electron gets in a high field region, even if it scatters around, it's very hard for it to get back out and work against the field and get over the barrier. So once it gets in that region where there's a lot of scattering and the mean free path is very short, the scattering doesn't affect the transmission. The electron is bound to come out the drain. The only place that scattering really matters is near the top of the barrier where the electric field is low. There is this short region under the control of the gate where the electric field is low. The electrons are injected with near equilibrium thermal energy. They have a mean free path that's close to the one you would deduce from the mobility. And if they backscatter there, it's easy for them to return to the source. So the scattering in that little region, which is just a small fraction of the channel length, that's a bottleneck. That's where the scattering matters. Okay. All right. So in order to fix this, we could think scattering only matters in this little region script L. So I should just take my transmission expression and I should just replace the actual channel length by the length of this critical region. All right. Now that's a little, how do you know the length of the critical region? Right. This is where I think you need a detailed simulation. You need to solve the whole transport problem self-consistently, get the right energy band diagram, and then you can see what that region is. But qualitatively, we can understand that that's going to be a short region, some fraction of the channel length, and that means that the transmission in the saturated region is going to be mean free path over mean free path plus the length of that region. And since the length of that region is so much shorter, the transmission is much higher. Now, another question here that comes up is, should we be using the same mean free path in both cases? And to first order, the argument is you should. And that's because if I look at the dotted line, the carriers are just coming in with thermal equilibrium energy. They have low energy, and they have some mean free path. If I look at the solid line, where the scattering matters, the electrons were just injected with thermal energy. They don't have an electric field that's accelerated them. They still have small energy, about the same mean free path. So the surprising thing is that under both low bias and high bias, I should use the same mean free path. That mean free path is related to mobility. So that's the argument that mobility still has some relevance for these small devices. Okay, so that kind of argument explains why the transmission is higher when we have more scattering, which is a little counterintuitive. So we should also mention, when we talk about operation near the ballistic limit, what does that mean exactly? It doesn't necessarily mean that there's no scattering in the device. There might be a lot of scattering in the device. What I mean by that is, it's the current that we're getting is close to the current we would get if there were no scattering. Right? And that's a little bit different, because you could have a lot of scattering in the region of the device where the carriers are very energetic. And if the device is designed properly and is electrostatically well controlled, then that scattering won't have much effect. Right? It's only the scattering in that little region. So if that little region is near ballistic, even though there's a lot of scattering in the rest of the channel, you'll get the near ballistic current. So when we say that the device is operating near the ballistic limit, we need to be clear that there could be a lot of scattering going on. Okay. And then this question I mentioned briefly, another big question that, well, at least of a dozen years ago, experimentalists always, they look for a few parameters that they could work on that will improve the performance of the device. And one easy parameter to get a hold of is mobility. So you can do things like you can strain a semiconductor and get high mobility. You can look at different materials and get high mobility. You can do things like that. You can look at quantum confinement and see what that might do for you. But mobility is always, it's a concept. If you understand transport theory, you say, you shouldn't be talking about mobility at these length scales, when electric fields vary so rapidly. It's not a well-defined concept. But yet, it always seemed to steer people in the right direction. If you work on mobility, the performance of your nanoscale device improves, right? And I think we can understand why now. It's that the mobility is related to the near equilibrium mean free path. Okay. The backscattering in this critical region is controlled by the near equilibrium mean free path, since they haven't yet been accelerated by a strong electric field. And therefore, you can relate the mobility to the on current, because it's a measure of the mean free path. But, if you look near the drain end, those mean free paths are really, really short. You wouldn't want to, if you wanted to try to reproduce that velocity versus position profile that I'd been showing from the Monte Carlo simulations, you could never do that with a mobility. It's just, under conditions like that, the concept of mobility just doesn't make much sense. But in this context, we could say mobility is directly relevant to the on current of a nanoscale device. Okay, now what I want to do is to connect this back to the traditional model. We did that for the ballistic model, and then we can do it one more time for the scattering model. So this is our traditional expression. This is the expression that we have from the Landauer approach. They look very much different. Okay. The transmission is related to the mean free path. The mean free path is related to the mobility. Okay. So if I do a little bit of algebra and rearrange things, I can make that second equation look different. Okay. In fact, I can make it look like this. All right. So that looks like the traditional expression, except that I replace the channel length by the channel length plus mean free path. Okay. All right. Just algebra, right? That's all it is. Now that's kind of nice, because now as scaling takes the channel length to 0, you don't have to worry about things going to infinity. They'll go to some finite answer. And, you ask, well, why in the ballistic limit, when the channel length goes to 0, is there a mean free path downstairs? But remember, there's a mean free path in the mobility. The two just cancel out, and there is no mean free path in the ballistic limit. So you could write it that way. Or you could write it another way, just rearrange the algebra a little differently. You could write it this way, just like the traditional expression, but instead of the actual mobility, we'll have an apparent mobility. Okay, just comes from rearranging that equation. And that apparent mobility is defined by 1 over the apparent mobility is 1 over the effective mobility plus 1 over the ballistic mobility that we saw earlier. And it just says whichever one of those mobilities is smaller will dominate. So if the channel length, and remember the ballistic mobility depends on channel length. So when the channel length gets very short, the ballistic mobility can get very small. It can dominate, and the apparent mobility will be the ballistic mobility, not the mobility that you would get in the bulk semiconductor. Okay, so that's very nice. There's this very nice, simple connection. We can make the model of the 1960s work today just by doing this simple replacement. And there's some physical justification behind it all. It's not just ad hoc empirical, it makes sense. Okay. By the way, some of you might have seen something. This is known as Mathiassen's rule. If you know the mobility due to ionized impurity scattering, and you know the mobility due to phonon scattering, and you want to know what is the mobility of a sample that has both ionized impurity and and phonon scattering, the way you do is you combine the two this way, right? And the lower one is the one that ends up dominating. So we're finding the same kind of thing. Okay. The effective mobility is something you can measure on a long channel device where there are no ballistic effects. And the ballistic mobility we can compute, right? It's this channel length dependent thing. All right, so we've got a good solid theory. Now, what about saturation? You know, what happens in saturation? We have this traditional expression, and we have this scattering expression that, again, looks a lot different, you know, but we know that the transmission is related to the mean free path and the length of that critical bottleneck region. Okay. So again, we can do some algebra and try to eliminate t and make that second expression look more like the first. If you do that, this is what you'll get. W, you see the W there, the C there, the Vg minus Vt. Instead of Vsat, we have 1 over the thermal velocity plus 1 over diffusion coefficient divided by the length of that mean free path. Okay. Now, the length of that bottleneck region. All right, so that actually makes a lot of sense. So let's take a look at that. So here's the picture we have. That white area there at the top of the barrier, that's the bottleneck. That's where the scattering matters. And what we've deduced is that the average velocity in that region is given by the smaller of the ballistic injection velocity, that's V sub t, the thermal velocity, or d over L. And what's d over L? You know, it's got units of velocity. D is centimeters squared per second, right? L is centimeters, so it's got units of velocity. You know, you can think of it as the average velocity that carriers are diffusing. When carriers diffuse across a region of thickness x, with their average velocity is d over x. Right? All right. So that's the average velocity of carriers that are diffusing across that regime. Now, you worry about Fick's law. When things get very, very short, that average velocity d over L would increase without limit, right? Physically, it can't go above the thermal velocity because diffusion is random thermal motion, right? So we can't let the diffusion velocity go above that. That's what this formula does, is it says that, well, the average velocity, carriers, in order to get across that low field region where there's a small electric field, carriers diffuse. They diffuse across that thin bottleneck region, but they can't diffuse faster than the thermal velocity. So when the region gets very short, then the 1 over Vt becomes important, and we're at the ballistic limit. So you sometimes see in textbooks that under high bias, the current in a MOSFET is a drift current. But I don't agree. I think it's a diffusion current. You diffuse across this thin bottleneck region. In fact, this device looks just like a bipolar transistor. We get back to that old paper in 73 by Ed Johnson. It said that these are really the same devices. So, if you look at that bottleneck region, the carriers are diffusing across that. That's like the base of a bipolar transistor, for those of you that know bipolar transistors. The source is like the emitter. So electrons get injected from the emitter into the base. They diffuse across the base. The high field part of the channel is like the collector of a bipolar transistor. It just collects the things that come out of the base. And you know, we're very used to, when you compute the IV characteristics of a bipolar transistor, what you focus on is the base, because that's what limits the current. You know, except, you know, there are some effects that become important at high bias and things in the collector, but where you start with is diffusion of carriers across the base. Once they get across the base, they just get swept out the collector. So that's the bottleneck. So we have the same kind of bottleneck in a MOSFET. The device is really very, very similar. Okay, so, you know, we showed this virtual source model that is semi-empirical. but that is now being used more and more for exploratory transistors and nanoscale transistors. But its development was based on traditional concepts, and then we just went in and adjusted some of the parameters so that it fit data, and it fit remarkably well. And now we understand a little more what we're doing, that these two key parameters here are really not physical at these length dimensions. So what we have to do is to replace those two parameters by the appropriate parameters for nanoscale MOSFETs. Once we make that replacement, then the rest of that virtual source model works just fine. And we can treat nanoscale devices. Okay, so, that's the story for semi-classical nanoscale MOSFET. The scattering reduces the current. That's kind of obvious. What isn't so obvious is that the effect of scattering is stronger at small bias than at high bias. And what maybe wouldn't have been anticipated is that these expressions we develop, that go all the way back to the 1960s, continue to work if we just replace some of the parameters with appropriate physical parameters for small devices. So that was really a bit of a surprise.